Good afternoon, this is Schweitzer, and this is our second video in a series of videos which I'm call School of Acid Base, and walks us through just a lot of topics in order on what we might want to or need to during acid base chapter. Now, we've already discussed the idea that anything that contains H3O plus ions is going to be acidic. Anything that contains hydroxide ions is going to be considered basic. But really, it's a teeter-totter on the quantity of these guys that are present. All right, and this sort of opens the door into, I guess, what could be considered some more complicated ideas, or something that may just be new to you. So, this next section I'm going to be describing is mostly, you might call a harbinger of things to come. It's just describing some things that for this video you don't need, but for future are very helpful. So if you were to open up a tap water and pour yourself a glass of water, what might this look like? You would think that you would just have water molecules, which is what you could live your whole life just knowing this, and no big deal. But scientists took a closer look at this, and they realized that really, water molecules are constantly breaking down to form hydroxide ions and H3O plus ions. So in this case, when this happens, you get one of each. So the net difference acidity-wise is nil, nothing, because you have one of each. They're still in the same concentration. We call this the forward reaction. Then, of course, these guys don't like each other at all. They're like what I would call He-Man and Skeletor. They're arch enemies. They react together and then recombine and form water molecules. This is the reverse reaction. So we have this back and forth battle, and eventually that back and forth battle becomes a bit of a stalemate. And the stalemate in chemistry term is called equilibrium. Now, whenever I deal with equilibrium or the stalemate, I often refer to this little book here, this little dealie called, I draw this little chart. I may draw this a couple hundred times a year, and this describes the stalemate, and it's a little gauge. If you're right up in the middle, means you have when you get to your stalemate, you have equal amount of your products as you do reactants, which means the forward reaction was as prevalent as the reverse reaction. But if you end up with, let's say, more products that at stalemate, then we would be called product favored. Again, this is a lot of stuff that we'll be using later on in this chapter. And then if you end up more reactant, then you'd be called reactant favored. And to do this, get this actual calculation, what we do is we use a K value, which ends up being, this is a qualitative way of looking at it. Scientists, they like qualitative, but they want quantitative. Give me a number that can describe where I'm at. So they use this method called equilibrium constant. And what they do is they track, in a simple sense, the concentrations of products divided by the concentrations of reactants. And this gives you a number. So if your number is 1, then you would be right in the middle. If your number is greater, if your K value is greater than 1, then you're somewhere over here. K is greater than 1, meaning I have more product than I do reactants. And if your K is less than 1, then you're over here someplace where K is less than 1. This one, again, is called product favored. And this is called reactant favored. We'll be using this a whole bunch as we move through this chapter. So if I were to track this guy, the way I actually write this, again, since we're tracking concentrations, the products for my K value are equal to, what we do is we take the concentration of the hydroxide ions and the concentration of the H3O plus ions, and we actually multiply these together. This is just the way they do this. Okay. and then you divide it by the concentrations of your reactants. Well, in this case, it turns out that the liquid water actually doesn't have a concentration. Any pure liquid doesn't have a concentration. So that being said, there's just a 1 here. And then we call this expression Kw. This is a very useful expression, and lots of chemistry students are using this particular situation all the time, this math formula all the time, and may not realize that this is what's happening to get that formula. So let's use the formula at this point. Now, a couple of things you might want to note about this. Okay, what this means is that, okay, well, first of all, at the K value is temperature dependent. So at 25 degrees Celsius, Kw equals 1.0 e to the negative 14th. So this number is going to be static, 1.0 e to the negative 14th. And that means that, okay, well, that equals the concentration of my H3O plus ions times the concentration of my hydroxide ions. Now, if this number is static, algebraically, it means that, okay, we can have a situation where we have in the solution present lots of H0 plus ions and a very small number of hydroxides. Those multiplied together could equal the Kw. Or we could have them be equal. Or we could have lots of hydroxide ions and maybe a small amount of H0 plus ions. Either way, in this sense, we always have hydroxides present and we always have H3O plus ions present. It again is just a teeter-totter. If I have lots of H3O plus ions, I only have a very teeny amount of hydroxides. And if I have equal amounts of these two guys, then in this case it would be neutral. And if I have lots of hydroxides, I'd be basic, and a small amount of H pluses, I would be, again, a basic. So that is mathematically, in reality, what's going on. We have the solution can only hold so many H plus ions and hydroxide ions, and that will never, when multiplied together, exceed the value of Kw. So let's look at our main idea here, okay? And that means, okay, am I acidic or am I basic, and how do I quantify that? Well, first of all, if you have this 1.0 e to the negative 14th, and what would be if they were equal? Now this is at 25 degrees Celsius, so what if we had equal amounts of both of them? What number, when multiplied together, if the same number equals that? It'd be 1.0 e to the negative 7th. Of course, you could do this algebraically. Doing this, 1.0 e to the negative 14th equals x squared, square root of this, and you can get x equals 1.0 e to the negative 7th. So this is the concentration when the hydroxides will equal the H2O plus ions. This is a neutral solution always, and that is important to realize, that 1.0 e to the negative 7th is what I call the tipping point. It's the fulcrum on which this little seesaw tips. 1.0 e to the negative 7th. Every time you get or see a concentration of an acid or a base, you want to put it on this mental scale. So for example, if I have a concentration that is 1.0 e to the negative 10th H3O plus ions, the first thing I do is I look at, okay, I know that if I'm neutral, my balance would be 1.0 e to the negative 7th. Did my H3O plus ions go up, or did my H3O plus ions go down? Looks like H3O e to the negative 10th is smaller than the midpoint, e to the negative 7th. Therefore, that means my H3O plus ions went down, and my H plus ions, my hydroxides, went up. Therefore, I am basic. All right. Again, you always have H plus ions and you always have hydroxides. Just because I only discussed the H0 plus ions doesn't mean that I only have these guys. Every single solution will contain both H plus ions and hydroxides. It's just a matter of how many. And this formula, 1.0 e to the negative 10th, e to the negative 14th, equals the concentration of H plus ions times the concentration of hydroxide ions, is our first big formula that's going to allow us that if I give you this guy, then what's the other half? There you go. First big formula. All right. Now, that being said, let's go ahead and draw ourselves a little map. I'm going to draw ourselves a little street map. H3O plus ion concentration, and we have the hydroxide ion concentration. And of course, we know that these teeter-totter off each other. And this is concentration of H plus ions times concentration of hydroxide ions equals 1.0 e to the negative 14th. All right, this is what happens in nature. This is all we need. But people have created a scale that allows us to maybe condense this into a little easier system. And one version of it's called the pH system, which just about everybody has heard of. This tracks the H3O plus ions. Again, if you're looking at a teeter-totter, you don't need to look at both sides of the teeter-totter to know where one side is relative to the other one. You know if one side's down, the other side's up. So we've become very accustomed to just tracking the H3O plus ions. We can convert this back and forth between these values. But there is an alternate system called the pOH system. It just tracks the hydroxide ion concentration. Let's do this. It works almost entirely the same. So let's review these two systems. The pH system starts out 0 being very acidic, 7 being neutral, and 14 to be very basic. Okay, so this is my acid range. This is my basic range. Well, the pOH system is the mere opposite. A 14 is going to be very acidic, a 7 is neutral, and a 0 is going to be very basic. So this is how this scale works, and it doesn't take a real math genius to see, oh, it looks like the pH and the pOH always add to 14, and it does. So at 25 degrees Celsius. So we now have a conversion between these two systems, which is the pH plus the pOH equals 14. Okay. Now, again, it's just a mathematical algorithm that flips pH to pOH to H plus concentration and vice versa. Now, in this situation, we don't use a linear scale, and in chemistry we've been using lots and lots and lots of linear scales. This is what's called a exponential scale, which means that if I have a pH, okay, that is 0, that means I'm getting a 1 molar concentration of H plus ions. And this is really important, and kids who get more and more advanced into chemistry need to be able to flow through the pH system without doing the math and just doing some estimates. And this is how it works out. We have pH of 0 is 1. 1 molar. If I have a pH of 1, then I have a 0.1 molar concentration of H plus ions. Remember, the pH tracks the H plus ions. It works the same way for hydroxides. Same numbers. If I have a pH of 2, then I have a molar concentration of 0.01 H plus ions. And this is in moles per liter. pH of 3 is 0.001. So you would note that the deviation between here is, actually between the first two, is 0.9. Alright? And the difference between 1 and 2 is 0.09. And the difference between 2 and 3 is 0.009. So it's not a linear scale. And in fact, if you were to take the pH, okay, let's say the pH of 0 is 1, so the pH of 0 is 1 molar. So 1 molar concentration gives you a pH of 0. A 0.1 molar gives you a pH of 1. A 0.5 molar, is it going to give you a pH of 0.2 of 0.5 of 0.5? No, it's 0.3. It's not a linear scale. That's the first thing that you want to kind of get in your mind. Okay, it does not work. It works off essentially with powers of 10. Okay, and so it's working off some power of 10. Okay, how many times do you multiply 10 together to get a number? That's basically what we got here. And it's just a mathematical algorithm. And this, reciprocal, or I should say not reciprocal, reversed, would be the log system. Log base 10, which basically says, okay, how many times do I got to multiply a number together by a number of 10 to get that number? So in this situation, the mathematical formulas to get from concentrations, and it could be either concentration to this p value, or pH or pOH, is the negative log of the concentration equals the pH. Negative log of the concentration equal, in this case, if I'm using hydroxides, pOH. These formulas are identical and are located on any advanced placement sheet. And are critical for maybe being on a note card for any chemistry student. Okay, and then to reverse this thing, of course, like I mentioned, it's an exponential system. If you hit your second button on your calculator and hit the log button, your calculator will automatically pop up this. So if I'm going to reverse this system, I type in the second log, which is 10 to the negative pH equals the concentration of H3O plus ions. Okay. And then the other guy is just 10 to the negative pOH equals the concentration of hydroxide ions. Okay. And we therefore really only have one, I should say, rather, 1, 2, 3, and 4 different formulas. These two are the same as this one is doubled right here. So there are 4 different formulas. And you should be able to, given any one of these guys, move amongst them mathematically and find all their corresponding parts. Generally speaking, this is one of our first quizzes that we might have in chemistry. And we will do a quick follow-up video to test out these particular formulas. Other than that, thank you very much.